host, Dr. White. A couple of things I should talk about. One is, don't forget the deadline for the extra credit project is this Thursday when I walk out the building. I will try tomorrow to get here early, 30 to 45 minutes early, at least 30 minutes. So if you want me to check your extra credit project before you hand it in by Thursday, come on down. All right, a couple of things. If you noticed your email over the weekend, actually Friday, when did I post it? Friday morning, you'll see I posted for test number 4, which is this Thursday. Test number 4 this Thursday covers polymers, lipids, carbohydrates. Test number 4 has 9 pages, 20 problems. Some of the problems have multiple parts. The points breakdown is general, wow, 59 points. Nomenclature 10, reactions 39. What's that? 59 points of general knowledge. Well, let's look at this way. If I ask you, is my right hand chiral or achiral, or is it a chiral object or achiral object? Well, it's not nomenclature. It's definitely not a reaction, so it must be general knowledge. Also, if I ask you, draw the enantiomer of the following molecule. Well, it's not nomenclature, it's not reactions, well, it must be general knowledge. And that's why it's so high. And as always, my tests, if you've done the practice problems and kept up with the lectures, you should have no problems. Every concept, every question on the test, the concept behind that question, I've discussed at least twice in class. And if you know your stuff, which is the way all my tests are, in other words, if you practice and study, you should be done in about 35 minutes. If you haven't, well, I'd give you all day and you still wouldn't know. So, anyways, I don't change my ways. And any questions on test 4? It'll be this Thursday. Well, if my memory serves me correct, and luckily it still is sometimes, I promised to do the practice problem on lipids. So let's go through it. By the way, over the weekend, even though we had a lot of rain, my hearing is still the same. It didn't affect it. So remember, letters of the alphabet are hardest things for me to pick up because I can't guess like I can with regular words. All right. You can tell it's the end of the semester, Dr. White's getting lazy. And what is a lipid? C knows. Well, let me tell you, what is a lipid? That's a molecule that comes from a plant or animal that's not soluble in water and soluble in nonpolar solvents. Again, a molecule that comes from a plant or animal or something that was alive, you can put that down, that's not soluble in water, but soluble in nonpolar solvents. You can, instead of saying nonpolar solvents, you could put down something like hexane, octane. Even gasoline is nonpolar for the most part. All right, next one, number 2. Name one type of lipid. Actually, there are more answers than I have there. What's a lipid? Well, I just told you. And what are some examples? First of all, you could put down fat, you could put down oil, put down steroid, you could put down hormone. And then 2 other answers, I was thinking about this morning when I was checking through this, that you could have put down would be, I guess one type, also you could have put down saponifiable lipid and non-saponifiable lipid. Those would all be correct answers. Remember, saponifiable lipid is a lipid that upon reaction with base, alkaline conditions, yields carboxylate anions of fatty acids, otherwise known as a fat or oil, which I have. Then a non-saponifiable lipid does not react with base and water. or under alkaline conditions, and we call those the steroids or hormones. All right, let's continue on. What's the difference between a fat and an oil? A fat is a solid or semi-solid at room temperature, and oil is a liquid at room temperature. For those who must know, room temperature is 25 degrees C, but you don't have to put that down. I'm going through some important ones, so I'm having a good time, so I can go through more of them. It's a short problems, but we'll see. All right, what's yellow grease? Pig's fat. Again, because I worked in this industry, you get that additional knowledge you would get from other teachers here. What's white grease? Pig's fat. What's tallow? Beef fat. All right, let's do some reactions, some chemistry. And here, instead of putting R prime or R sub S or O here, I just picked some representative R groups that are not realistic, but still give you practice. All right, give the organic product or products for the following. And you look at this, and the first thing you've learned to do this semester when you see an organic molecule, what functional groups are you dealing with? In other words, what is different? And notice you have ester, 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 and double bond. Reacting with sodium hydroxide and water. You know reaction with double bond with sodium hydroxide and water? I don't. But ester-based water gives you an alcohol plus the carboxylate anion of the carboxylic acid that would have used to make that ester. Triglyceride gives you glycerin, each alcohol from each ester. First ester gives you this, second ester gives you this, and here the R group on the third one, 3 carbons, which is not realistic, but I figured by then you need tighter graded carbons, so I gave you a break, and I did. All right. Continue on, same molecule, now we're reacting with acid and water, H plus is acid. What is this? Acid hydrolysis of an ester. Get back the alcohol and the carboxylic acid you would have used to make that ester. And notice each ester gives you an alcohol, which again you get glycerin. R in the first carboxylic acid is that. R prime is this. And the third ester will be that. Remember, as always, these answers are available to you 24/7 on Blackboard, assuming schools' computers are up, and assuming your computers are up. Yes, Britt?
So if they're not attached to the OH, is it like separate?
Which one?
The HO, sometimes like,
All right,
The middle one?
the middle, this is
Yeah.
on that carbon.
no, I mean, like, is it attached to OH? Yeah, like those.
This is glycerin. And the answer to the question I think you're asking is yes. Let me draw it on the board. Glycerin, as you learned from the alcohol, does that clarify?
What I mean.
Oh,
Like, is it?
are these separate molecules?
Yeah.
Yeah, you get, this is one molecule glycerin, then you get this carboxylic acid,
Okay.
and this one. I guess it's sort of hidden here. This is a dual purpose plus sign. In other words, I got lazy. Does that help?
Yeah.
And by the way, if you were to write the answer with no plus signs, I'd know what you're talking about. So, did I tell you organic chemists are lazy? Sloppy sometimes. All right, let's continue on. And here, what do we have that's different? 3 esters and still a double bond. What are you reacting it with? Hydrogen and catalyst. And it seems like long ago, in a galaxy far, far away, you learned double bond, hydrogen and catalyst. Catalyst can be nickel, platinum, or palladium. You break the pi bond, and each atom of the double bond gets a hydrogen. Does anybody here know a reaction with hydrogen and catalyst with an ester? Because I don't. In other words, doesn't react. And that's truly the beauty of functional group chemistry and organic chemistry. Things that don't react, guess what? Stay the same. And therefore, the only thing that's going to change is this double bond. Everything else stays the same. And notice Dr. White was being helpful. Look, and you see, you break the pi bond, carbon gets the hydrogen. And I just put a different catalyst in on the next one. Same thing. All right, let's look at E. E is where you have a triglyceride, which is 3 esters, and you're reacting with steam. What is steam? Hot water. What are ways of making a reaction go quicker? One, use a catalyst, such as acid or base, as you've seen with triglycerides. Or two, by increasing the reaction temperature, the reaction for most reactions will go quicker. There's a rule of thumb, this one, not a law, and that is for every 10 degrees Celsius increase in the reaction temperature, the reaction rate doubles. So using steam will make it go much quicker. And what happens, ester steam is same as acid hydrolysis. Get back the alcohol and the carboxylic acid you would use to make that ester. 3 esters. Oh, this time I remember to put the plus. But anyways, here, first one gives this alcohol plus this carboxylic acid because this does not react with steam. Second ester is this alcohol plus this carboxylic acid. And the third ester is this alcohol. There should be a line there, it's an H. And this carboxylic acid.
Dr. White,
Yeah.
I'm drawing a blank, so I want to make sure I'm correct on this. R prime OH and ROH are 2 separate things, right? Okay.
Think of R like in here as this X and Y. And if I have I could write it this way, but what if I did this? Doesn't really change anything. And all R prime and R double prime are X and Y. What's X and Y in math numbers? And what's R and R prime in organic chemistry? Carbons and nitrogens. And that's it. Sometimes it can be a little more complex, but usually it's that. It means there's another part of the molecule. And in organic chemistry, that means carbons and hydrogens. Good question as always. I'll question. All right. Now, if you remember, to give you a real-world experience, which I try and do always in here, this is a triglyceride. R could be different, the same, but to show what's real life with either white grease, yellow grease, or tallow, what is that realistically? 50% saturated fats, fatty acids, what the R group is from the carboxylic acid coming from this, and roughly 50% unsaturated with a double bond. Well, how can you show 50-50 with 3 things? Mother Nature found a way of doing that, but that's more complex. So to simplify it, I have defined tallow, white grease, as this, where this is, you can have 2 of them sterile, 1 allele, or you can do the other one, but I like SOS, my personal little joke. And remember, R sub S and a carboxylic acid, stearic acid, which is this structure. So when I say R sub S, I'm really saying that for a sterile group. And R sub O, that would make this carboxylic acid, fatty acid, is really oleic acid. Which has this structure. And R sub O is that. And therefore, this is a good representation of tallow, white grease, or yellow grease. So, I'm test. Yes, ma'am.
Okay, so for what you just went over with the R subgroup S, subgroup O, subgroup S, when doing the reaction portion of it, how you have, I was confused on the answer part.
All right, I know your question.
Okay.
Let me see if I'm going to guess it. Let's see if Dr. White's good. By the way, that reminds me of, how many of you have ever seen, let alone heard, of Johnny Carson's show? They used to have a thing called Tarmac, and you'd have an envelope with a question, and you'd give the answer, and then his sidekick, Ed McMahon, would read the question. Let's see if I can do the same thing. All right, now let's look at the first question, F. It says remember it says give the organic product or product for the following. Now, it says yellow grease, H plus in water. Ooh, what do? I don't know how to react a word with H plus in water. No, this is the structure you should use for yellow grease. This, R sub S, R sub O. Now, when do you use this? If on a test I ask you draw the structure of oleic or stearic acid, which you should know, then I expect you to draw it with the carbons. If I give you a name like this, or if I put it like this, then you could use the R sub S, R sub O, R sub S. Is that what you're asking? Sort of.
For the oleic acid, what's attached to the seat? I just can't see it because of the screen.
I'll do my imitation of Dr. White holding the screen against the board. Look out, it's totally awful humor 1st of May. I'll never say that again. So, got it? Keep on the wall, got it. Going once, twice, all right. So let's take a look at this. The question is, if on a test I were to put yellow grease, H plus water, what do? First of all, you're only supposed to give the product or products. You don't have to write this, but you should know this triglyceride, which is a triester, acid, water, you get back the alcohol and the carboxylic acid you would have used to make that ester. First ester, this hydroxy group on glycerin, stearic acid. That will R is R sub S. Second ester, this one, middle alcohol glycerin. This will give you R sub O as your R group on the carboxylic acid. Now, on my test, I ask give the organic product or products. I don't ask you to balance it. If you notice the last ester gives this final hydroxy group on glycerin, and you get stearic acid again. If it makes you feel good or better, you can write this again, or leave it like this, or put a 2 in front of there. Because the question asks, what are the products? And the products are glycerin, oleic acid, and stearic acid, which I've shown. Now, being a sneaky person I am, oh gee, next one, tallow, acid, and water. Guess what? This is the same structure used for yellow grease, white grease, and tallow. Therefore, you get the same answer. And once again, white grease. Again, this is the same structure used for tallow and yellow grease, and now white grease. Therefore, you get the same answer as F, same reaction. In real life, that's essentially what happens. All right, let's look at yellow grease with steam. What do you have? A triglyceride and steam is the same products as acid hydrolysis, which would be glycerin, stearic acid, oleic acid, and you get the same as F. Same thing with tallow. Now let's look at K. If I'm going too fast, someone say, slow down. And remember, these answers are in Blackboard. K, yellow grease, sodium hydroxide, and water. What's the general reaction? Well, what's in yellow grease? By the way, what functional group are in fats and oils? Esters. And here's yellow grease. What is it? Ester. For test number 3, you learned ester, sodium hydroxide, and water. Gives back the alcohol you would have used to make that ester, and the carboxylate anion of the carboxylic acid you would have used to make that ester. First ester, this hydroxyl group, you get sodium stearate, because R is R sub S. Second ester, you get this alcohol, sodium oleate, because the R group is R sub O. And the last one, once again, you'll get this last alcohol, glycerin, plus R is R sub S, but we've already wrote sodium stearate. So if you want to write it a second time, feel free to. You don't have to. And finally, on reactions, give the organic starting material and materials, which I can't put. I think I have one on the test, but I can't remember right now. And question is, notice, give the organic starting materials, and I didn't say you have to draw it, but here, you react something with sodium hydroxide and water. What do you get? Glycerin, sodium stearate, or oleate sodium stearate. Once in a while I forget, and I did on this one. Let me just remind you. These are both the same. Every bend in the line is a carbon. And I've been pretty good this semester. I've stayed away from it. Normally at my level, we don't write in carbons, but it's easier for you to learn, and that's why I'm here, for you to learn. And therefore, what gives glycerin, sodium oleate, sodium stearate? You notice above, same products. The answer would be tallow, yellow grease, white grease. You could do it that way, or you could write the actual triglyceride. And finally, hidden away at the very, very, very bottom is what is a surfactant? And that's a molecule that interacts at the surface of things that has a nonpolar tail, polar head. And last week, we all had a lot of fun investigating surfactants and bubbles. By the way, pictures came out really good. I'm going to start blackmailing people next week. No.
I have a question about the surfactant. Okay, so the bubbles that we did in lab last week, was there only one surfactant in it or multiple?
Well, in real life, hand soap has more than one surfactant, but I was just looking at the key surfactant.
Yeah, well, the reason
And the same thing also with the Dawn, and it all usually has other answers, usually one surfactant.
The reason why I was asking is because I was looking at the bubble, no, the, like, a bubble bath label, and there were multiple surfactants.
Yeah, and if you looked at some of the formulations that people use in their own formulation, they put in hand soap along with Dawn. And a couple people tried all with one of those. What I was doing was trying to keep one variable at a time. I don't know if I mentioned it, but last week I also did this lab at the other school, and someone had a, I can't remember the exact formulation, I can't do the lab yet, remember this too, but they had a bubble that lasted at least 4 to 5 minutes. It was just amazing, with the air currents and everything. Everybody stopped and was watching this bubble. It was just, like, for a while, it just hung here, just like this. And it was a perfect bubble you've ever seen. All right, before I leave, any questions on this problem set? Well, I have a question for you. I assume between the last time we met in lecture and today, I hope all of you washed your hands at least once, and I see some smiles, so I assume you did. What happened? How did soap work? And these are one of those things I would like you leaving my class knowing how does soap work. And the first thing you have to know is what's soap. And soap has a non-polar tail and a polar head. If you look right here, when our, do I still have it on the board? Yes, I do. If this is a carboxylate anion, not a carboxylic acid, this would be sodium stearate, sodium oleate, as you saw in the bar of soap. Also sometimes the mixture is called sodium tallowate, and that's your bar soap. That's your factor. And most of your soaps come from either vegetable oil or animal grease, animal fat, or grease, yellow grease, white grease, tallow, unless it's a detergent, and then it comes from petroleum.
I actually looked on my husband's bar soap over the weekend, and sure enough, like the fourth ingredient was tallowate.
What?
I looked on my husband uses like.
It says sodium tallowate?
Yeah.
That's, how should I say, I don't know, common or marketing name for a mixture of sodium stearate, sodium oleate, and some other smaller chain links like sodium palmitate. Also, we would include sodium oleate, sodium oleneate, and sodium olenolenate. I have to say that. And oleic acid.
Here.
Yeah.
So is he bathed in like beef fat then? Do I need to buy him different soap?
I would say if it says sodium tallowate,
What's that?
it's coming from tallow, which is beef fat. The company I work for, we would buy 2 to 3 million pounds a week of mostly tallow because it was more prevalent. Americans eat more beef than they do pork, and therefore it's more available on the open market. But whenever we could get yellow grease and white grease, which might be in that bar too, but think of it, it's been heavily reacted, purified before you ever get to it. So it's just a chemical. Well, if you're what would I call it, a vegetarian or don't like in any way harming animals, then I don't know if there are any vegetable based. You might want to look at Neutrogena or something like that.
They're
But
probably like
if it says tallow, guess what? It came from some sort of animal fat. And that I bet my wallet on, and I only bet when I know I've won. Anyways, back to how the soap works, which does come from beef fat, a lot of it. But that's how the settlers made it. They boiled up lye, sodium hydroxide, beef fat, and in a big pot with water over a campfire, made their soap. Anyways, back to soap. Soap, non-polar tail, polar head. let's magnify that big piece of dirt that was on my hand. I want to get it off. And what do I need to know? First of all, I need to know the most important part of the puzzle. The most important part of knowing how does soap work is light dissolves light. Notice I use a small font to show that. And what that means is things that are polar are soluble in polar things, things that are nonpolar are soluble in nonpolar things, and the two don't mix well. They don't dissolve. And what's nonpolar? Dirt and grease, which we're trying to get off our hands, or other things. What's polar? There are other things, but this is an important thing. Water. Now, because of light dissolves light, so the nonpolar tail says, I'm comfortable with nonpolar stuff. The polar head says, I'm comfortable in polar things, and therefore, you use your soap, your water, your dirty hands, you go like this, and the molecules of soap see the dirt and say, oh, dirt, you're nonpolar. My tail is nonpolar. Let's line up this way because of light dissolves light. But not just one molecule, lots of them. I'm not going to show them all. And it totally surrounds the dirt particle to form which something you should know, a micelle. Now, micelle surrounds the dirt such that water, as it comes along, only sees the polar heads of soap. And water says, oh, micelle, I'm polar, you're polar. We both know light dissolves light. So let's go down the drain together. And they do, and now my hands are clean. And same thing with my clothes, my hair. If I wash the floor or something this weekend in my house, same thing. And you should know how soap works. Now driving here, thinking about the problem set, I realized there's something I forgot in fats and oils that I should have covered, which I will do right now. And again, this is something you should know. And you should know, leaving my class, a couple things. One, how does soap work? Two, how to describe with words and a general reaction what happens when you consume a fat or oil. And what's the general reaction? How do you describe that? Well, if you chew your food before you swallow it, or you'll choke, like my mother taught me when I was about 2, because I did, and it goes down into your stomach. What's in your stomach? Acid and water. What functional group is in a fat or oil? An ester. So with words, you guys see the R here? What happens when you consume a fat or oil is acid hydrolysis of an ester. What's the general reaction? Write it a different way. But for test number 3, and also in this chapter, you learn ester, acid, and water. You get back the alcohol you would have used to make that ester, plus the carboxylic acid. So this is the general reaction that occurs when you consume a fat or oil. I remember one of the questions I always tell you should ask, why am I learning this stuff? Well, now that you know esters, and now that you know fats and oils, you know what the reaction is going on inside of you. And I hate to break it to you, but you're walking organic chemical plant. There are a lot of reactions going on right inside of your stomach, another place in your body, and that's for another course to cover. All right. And I'm going to be subtle today. Now, while we're talking about general reactions and things you should know, and I already discussed this, but it won't hurt to discuss it a second time. Another thing I would like you to know, leaving my class, now that you've learned organic chemistry, is what happens when you eat a carbohydrate. And what functional group is keeping glucose together in a carbohydrate? An acetal. And therefore, when you eat something with a carbohydrate, like if you had your Captain Crunch this morning, or if you had your, I haven't had that in decades, but anyways, not that I need it either, or you had toast or something else, you chewed it, you swallowed it, went in your stomach, there's acid and water, and you should know how to describe it with words. And that's acid hydrolysis of an acetal. You should know the general chemical reaction, which you learned for test number 2. And this is for an acetal or ketal. You take this, react it with acid and water. You get back the alcohol and the ketone or aldehyde you would have used to make that acetal. You should know this general reaction leaving my class. By the way, both of these in test number 4, you should know them too. And again, notice, again, being subtle. Game plan this week, tomorrow, back by popular demand. By the way, how many would like me to do a review for the next test? Back by popular demand, I will do tomorrow the review for the next test. Wednesday, I'll go through the carbohydrate problem set. That's why I rushed today, and probably tomorrow I'll have some time, or Wednesday, I'll go through some of the carb stuff again, because I rushed through it because I wanted to get through it, give you your chance this weekend.
Can you step to the side, to the right, just a little bit? Thank you.
Where does my glasses still work? Long distance computing. All right. let's go back, a little review. Last week, I showed you that, and you don't have to write these down, starch is glucose that's connected together in an acetal linkage. That's what this is. Remember, I wrote on the board all the different glucose molecules and showed how they hook together. And therefore, glucose comes together to make starch. Starch is really a polymer of glucose, one of nature's natural polymers. And cellulose, which is you're writing on, is a different form of a polymer of glucose. And what this means that you should know is if on a test I were to ask, draw the structure or give the name, that's something new. Draw the structure, give the name of the following products. I would put that on the test. What am I saying? Take starch, acid, and water. That's acid hydrolysis of an acetal. And what's starch made up of? Glucose. And what you'll get is glucose. And if I were to ask the same thing of sucrose, sucrose is glucose and fructose bond together, and you don't have to know how to draw this, in an acetal-ketal linkage, and when you break that with acid and water, what you get is acid hydrolysis of an acetal, and here you'll get back glucose and fructose, and that would be the answer. Now, how many of you, and this is my personal opinion and I'm expressing it, so take it for what it's worth, you're not paying for it. But anyways, how many of you over the last number of years have heard certain mothers groups, and they do have a certain point, but they're missing the science on it, that have said, oh, bad food companies putting all that fructose, otherwise known as high fructose corn syrup, in my children's food, and it's causing all sorts of diseases, such as autism and all that. And I disagree with that. It's causing a disease. It's called being overweight because of the calories. And so what did the food companies do? They said, oh, we hear your pain. And if you look at it in the last year or two, what are they doing? They're replacing the high fructose corn syrup with sucrose. So guess what happens? The child eats that product with a tremendous amount of now sucrose and gets them addicted to sweet stuff, that's part of it. And their stomach, it takes more fructose. So you're just cutting down the amount of fructose by a small amount, but they're still getting massive amounts of this. And unfortunately, a lot of the people in those groups bought into, oh yes, thank you for hearing our problem and solving. No, they're not. The main thing is my personal opinion, sucrose like fructose, high calorie, and you consume a lot of calories, and I found out the hard way, you gain weight. And weight itself is a serious medical problem. Luckily, I've kept it down, not as much as I should, but at one time, I used to weigh about 65, 70 pounds heavier than I am. And by cutting down my calories, I've been good. Now, interesting product is called cellulose. It's a white powder. It comes from trees, paper, other places, plants. And if you notice on cellulose, it has, just like other sugars and starch, hydroxyl groups. And cellulose is cheaper than starch. And I think you've all seen products like candy and food that comes in that real crinkly plastic you think of, and it's called cellophane. And cellophane is a reaction of cellulose with these two chemicals to make this molecule. Why it's like that, don't know, I'm not working in this area, but this is cellophane, which is a reaction product from cellulose, which comes from trees and plants. And notice Google comes up real good. Now, if you take, again, looking at cellulose, I have a lot of alcohols there. You learn the reactions of alcohols. By the way, on these two things, switches off. I take an alcohol, and you learned this for test number 2, reacted with ethylene oxide. Notice I'll put on the hydroxyl group here. I'll replace the H with CH2CH2OH. Well, I can do that with cellulose. And what they call that common name is hydroxyethyl cellulose. And it has this structure where the OH group has been replaced with, on the oxygen there, CH2CH2OH. And it turns out this molecule is an excellent thickener. It makes things thicker. More viscous is the science term. Why would you want things thicker? Well, how many of you like your ketchup coming out nice and thick, or barbecue sauce? Look on the label. Now, one interesting product, and I'd say at your local Walmart, is personal lubricant, and that gel, like KY makes it, they take water and hydroxyethyl cellulose, mix it together, put in a few other things to make it feel good also. But this is the thickener in most of your personal hygiene or care gels, and that's what it's used for. And with that, I'm going to let you out. Tomorrow's lab, only have to do the first part and one sentence. Do the tincture iodide test.